So in our last Let's Take a Moment, we defined what the daughter and the parent isotopes are. So if you recall, that unstable parent isotope decays into the daughter, and it decays at a steady rate. And that is by far the most important thing here about this. Let me move to another slide. Let's come back to this for a second. So what I mean is it decays at a steady rate. Let's say I have a box full of uranium. But let's also say I have a tiny little test tube full of uranium. So this uranium is unstable, and it's going to start kicking off, right, those particles in order to become stable. So it's going to undergo radioactive decay. But uranium doesn't just wake up in the morning and say, gosh, I really want to get rid of 5 neutrons today. And then the next day say, man, I really want to get rid of 2. It doesn't do that. It kicks out these particles at a steady rate. So maybe it gives out a particle once every 3 days, or once every 10 days, or once every million years. It decays at a steady rate. So it doesn't matter if you have a box full of uranium or a test tube full of uranium, it decays at the same rate. So this is really important. So our radioactive elements, they decay at a specific rate. And that rate's going to be defined for each individual element. But the important thing is that radioactive decay is not mass dependent. It is time dependent. So like I said, so maybe uranium kicks out one of those subatomic particles every 1,000 years. That means it's not going to do anything on the 999th day or the 876th day. It's only going to do it on the 1,000th day. And like I said, it doesn't matter if you have 8,000 atoms of uranium or 1 atom of uranium. It's all decaying at the same rate. Which brings us back to why we can use half-life. So let's say here we have any element. We can use oxygen. So when oxygen-18 first forms, right? So let's say here we have a rock that has oxygen-18 in it. It's initially going to be all parent. Eventually, over time, it's going to decay. But it doesn't all decay at once. So what we can look at is the half-life. That's how long does it take for that isotope to decay into half. So here, let's look at this graphic down here. So let's say we start with 16 atoms of oxygen-18. How long does it take for us to have 8 of the parent and 8 of the daughter? Half and half. And that's going to be defined by each one. So let's say oxygen-18 has a half-life of, let's just say, and I'm making this up, let's say it has a half-life of 6,000 years. So every 6,000 years we decay into half. So that means right here where I see half parent, half daughter, that is 6,000 years. And in another 6,000 years, that parent is going to divide into half again. Right? So here this parent will divide into half. So there's another 6,000 years. And then another 6,000 years, right? Look at that, we only have 2 left. Right? So every 6,000 years that divides into half. So the way we can use this, right? So let's say, right, we know that let's just say this element has a 6,000 year half-life. Let's say I have a rock. And I take my rock and I take my sample and I put it into a scanning electron microscope. And it tells me that I have 4 parent atoms and I have 12 daughter atoms. So this is a ratio. So how many half-lives is represented by 4 parent and 12 daughter? Well, if we notice, this is 1 half-life. This is 2 half-lives. Look at that, 4 to 12. So I know that this rock has undergone 2 half-lives, which means that rock is 6,000 plus 6,000 years old. So I know that rock is 12,000 years old. And we can use this concept with everything. right? So some uranium has a half-life of 4.5 billion years. So that means after one half-life, that rock is 4.5 billion years old. Okay, so just knowing the half-life, we have to know the half-life in order to figure out how old the rock is. But this idea here in this diagram, right, showing you how it decays in half, this is going to be the same for everything. The only thing that's going to be different is the actual age, is the actual number. That's going to depend on our elements. So hopefully you can see now why using this concept of half-life is really important and how we can use it to age date our rocks.